Hi there. Thanks for your interest in this plugin. And this is a short tutorial for using the EvoMass because there are many requests for the help for in regards to how to use this in your design. So I make this short tutorial to have a quick start on how this plugin can work and how you can use this plugin in your design. So let's see. Let's disable this page. When you install the plugin in your Grasshopper, you will see this tab, and there will be free generated model and some tools for carry out the automation, design automation. And I think most people will use this the EvoMass for the building meshing generation. So I will spend more time on how to use this generating model in the first page. So this will here is a free generating model. It's the additive algorithm and the subtractive algorithm, and the third one is the model I used in one of my previous study, but I didn't spend a lot of time on this model. But you can use it to generate a kind of a high-rise building with some courtyard, and maybe this is not working for the Rhino 6. So I will, but I think the most important tool model is this tool one, and I will show you how to use the additive and the subtractive model. For the subtractive model, you will see the component is like this, and you click the setup, and here you will see the panel. And because this is like the general rule to create a building with the features of the subtractive form generation principle. So you have to first tell the component what types of the building you want this component to generate. So the component won't generate anything if you don't tell what type the parameter of the building you want to generate. So if you use the default number, like there are 20 in the span in the X direction, 10 span in the Y direction, and 10 floors, and here is other parameter, you can generate a very simple building with some like a courtyard and have some open floor, and then you can keep the shuffle the meshing to generate other random design. And if you want to change the volume of the meshing, the building meshing generated, so you can just change the parameter here. And for example, if you want to have a high-rise building, you can just decrease the span number and increase the floor number. So here you can get high-rise towers. And in most cases, they don't have a courtyard or atrium in the high-rise tower, so you can make this number 0 and to increase the horizontal subtractor number to make them have more features like this. So as you can see, they will generate the building without the courtyard. But if you want to only generate building with courtyard, for example, in a deep plan building, a middle-rise building, you can just make this number 0 and turn and get the higher number for the vertical subtractor. So here you can generate a building meshing with different types, different numbers of the courtyard or atriums. And here is also you have some parameter to change the size of this courtyard. For example, if you want to decide this courtyard or the atrium being larger, you can just increase this number. Oh, this is a vertical, sorry. So we turn to the default number, and you see here is the 2.4, and if you turn this to the 3.6, the courtyard or the atrium will become larger. And another very useful function in here is the boundary constraint. If you turn this boundary constraint off, and this vertical subtractor will break the boundary of the initial volume like this. And if using this function, you can generate the building massing with different floor plan, the footprints. So, for example, you can create some building massing like have an L-shaped plan or the U-shaped plan. And other useful function here is the sampling. If you don't, if you want to have a general idea what types of the building this set of the parameter can generate, you can just change. You can just using the sampling function, you can create whatever number you want to. But usually, you can just like a one row and 5 columns. So let's see what's going on. Yes, so you will have a very general idea of what kinds of the building massing can be generated in under this set of the control parameter. All right. And the other useful function here is the fixed void. The fixed void will allow you to change the footprint of the building stably, or you can insert a fixed hole that can subtract it from the building massing. Like if you set the starting point here is a 0, 0, and then have a 6 by 6 span hole in the building massing, you can generate this type of the design. Or if you want to have like the fixed precision atriums in the building, central in the building, you can change this number. For example, so you can see there will be a hole that will always there. There will always there. There's always a atriums in this position in the building. So this is the very brief introduction of the subtractive component. So I will move to the additive one to show you how the other component works. Similarly, you click the setup and then to create to click the generate, and then he will have the building massing created by the additive form generation principle. And similarly, you can change the number here to change the types of the building generated by this component. And if you want to decrease or increase the complexity of the building massing generated, you can change the massive number here. And in the additive algorithm, you can use the enclosure factor to control how this smaller mass will occupy or fill the volume you define. For example, if you change this to a 0.35, and this building will become larger. And if it's a 0.45, it will become more larger. Instead using the enclosure factor, you can also use the real size constraint. And if you use the real size constraint, all the this additive mass will be in this will be constrained in this range of the size. And this will be more useful when you use this this component for some smaller design, like kindergarten design or some villa design. Right? For example, if you have all right, another function that I provided in this algorithm is that you can control the area. So, for example, if you want to generate a building like this, and for example, the cost area is 20,000, and if you click this on, and for example, you will change to the 18,000, and the algorithm will automatically change address the size of each of the mass to make the area more closer to the target area, but this one is not very close. We'll change another one to see. Sorry. Or maybe it's too smaller to set this number. Maybe change to a larger one. Yes, that one is too small for this building. So if you change like 24,000, this algorithm will try to make the generated design closer to the target area value, right? So you can see the gross area of the generated design is always like 24,000 or the 23,000. Another function is that you can change the separation control, which can allow you to make this meshing more separate from each other. Usually, if you use this in a high-rise building design, this function will be very useful. Sometimes it will be easier to generate some crazy design, but don't be worried about that. You can use the optimization algorithm to screen this kind of the design from the optimization result. And all right, here this is the basically the necessary function you need to use when you use the additive and the subtractive algorithm. And here I will move to the optimization part. And here I have an example to show you how to establish a design optimization workflow using the EvoMass. Here is I use additive algorithm as an example. So the first step is that you have to connect for example, I want to optimize firstly you have to connect the geometry of the building into building performance simulation components in the random grasshopper. In this case, I use the Diva as an example. So at the beginning, you have to, for example, to let the Diva know the boundary of the building. So you can have the roof, and the external facade and internal facade. Internal facade is only when there is a hole in the building meshing, so you will have external facade and internal facade. So in most cases, the internal facade will be empty value. So here you can see this is the whole the surface of the building, and then you have to create analyze grids for the DY to simulate the solar irradiation. So in the building design, usually you only calculate the solar irradiation received by the external in the facade. So you just need to connect the external and internal facade here, and to as the basics for the grid. So when you done this and you can connect this to the DY. Here you have a scene object. This is the scene object, and this is the grid. And you can also you can just connect these two parts into the object and the grid, and then you will connect this to the, here is the radiation map. And we turn this toggle on. And here you will calculate the solar irradiation. And here you can see the result. And if you want to create a design optimization workflow, you have to convert this result into a one fitness value. So in this example, I use all the solar irradiation value in each of the grid and make a massive addition. So here is the result of this the additive value of all the solar irradiation value accumulate in this whole building facade. And if in design optimization workflow, you also want to have some sort constraint. For example, you want this design have a feasible gross area, so you will have a gross area control for the fitness. So in my opinion, for me, I usually will use the area control to set up a punishment function here to give a reward or punishment if the building cannot satisfy the constraint, the area constraint you set. And here you will get the final fitness number here. And after you finish all this, and let me delete this, and you can connect this one is the steady state island evolutionary algorithm to the generative path and the fitness component. And you click here, and you will see the input and output. And here you can control the direction of the optimization. For example, you want to maximize or minimize the solar irradiation of the building. You can change the direction here. And here is the parameter for the optimization process. Here you can change the number of the subpopulation and the size of the subpopulation and the tournament size. And you can see the whole iteration for the current parameter setup. And usually I will recommend you to have at least over 1,000 iteration, and 2,000 or 3,000 will be more appropriate. But if you just do a very quick study on the design optimization, you can just set maybe 600 is okay, and then if you feel the result is okay, you can increase this number to like 50 or 100. And after you set all this property, you can click the start here, and the optimization process will start. And they will change the building massing and to receive the new fitness number here. Okay, I won't wait for this to finish, and here I will stop the optimization process. And in most cases, if this finish, you can save the project, and next time you can load this save result and to regenerate all the building massing you create in the optimization process. And here I have already prepared for save project here. And if you load the project, and you will wait a while. It takes some time usually. All right, this will take a while to let the component to load the whole project, and once it has been loaded, you can see all the design generated during the optimization process here, and all the parameter here, and the fitness at the last one. And so you can click here and to make the fitness at the beginning of the list. And here you will have some different colors of the data. So this means that usually they will have improvement. It will be improvement solution or the best solution in some subpopulation. And if you feel here is too many options, you can just click here to only show the current population, which means that they will only show the survival fit individual in the desired population at the last generation. And you can also to change here, you can see the improvement solution here, and you can also change different islands to see each of the design in each of the islands. Because I use the multi-island approach, so the design in each island will be usually become more similar, but the design in different islands will be have a different will be quite different genotype. And here you can also have some information. You can see here is the chart of the fitness improvement progress trend line, and the trend line for the standard deviation in each of the islands or the subpopulation. And here, if you change global, you can see all the data or the trend line in terms of the 5 subpopulation. And here you can see the genotype distribution in terms of each of the islands. And you can also only change here, only show the only you can see the difference and the similarity between the best solution in each of the subpopulation. And here you can also see the improvement diagram. Here you can see how the whole population, the fitness improve considering all the subpopulation. And then if you want to regenerate any one of the design in this list, you can click here and to generate a model. But before you click the generate model, you need to disable this part. I don't know the reason, but maybe some bug here. For example, if you want, the another function is that you can click here to sort the fitness number. For example, if I want to generate the best one here, and actually it is already generated. And then now you can turn on this and make the simulation to calculate the solar irradiation again. And if you want to generate another one, similarly, you have turned this off and to create the other one, and then you can recalculate the result. Another function is that if you run the optimization, I will recommend you to save the GH file in a directory because during the optimization process, it will create some backup file for you. If you optimization is stopped or terminated by like a power failure, you can reload this in progress backup file and to restart the optimization. So if you're using other types of the optimization algorithm component in the Rhino Grasshopper, if you computer crash or something, you have to restart you will lose all the data, but in here you can reload this data and then to continue your optimization process. So I guess this is the end of this short tutorial. I hope this tutorial can help you to use the EvoMass. And if you have any further questions, feel free to contact me via the help email, or you can find me in many places. All right, thank you.